Hello, my wonderful AP Chemers. I hope your day is going well so far and that it is as wonderful as you are. We're going to talk about solubility today and the intermolecular forces that go with that. And so if you remember, we had discussed different types of intermolecular forces, and we said that in solids and liquids, because the particles are condensed or close together, the intermolecular forces are significant and they cause different properties. Or affect different properties. And so one of the properties we looked at was melting point, another one was boiling point. So another property that is affected by intermolecular forces is solubility. And last year, we kind of talked about solubility in very simple terms. We said like dissolves like. And what that means is that polar solutes dissolve in polar solvents. Ionic solutes also dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. But if you mix polar with nonpolar, they won't be soluble. Or ionic with nonpolar, it won't be soluble. So the idea of like dissolves like is that if there are charges or partial charges, like polar and ionic substances have either charges or partial charges. So if both substances have charges or partial charges, they're going to mix together. If both substances do not have partial charges, like nonpolar and nonpolar, then they're going to mix together. But if one of them has charges or partial charges and the other one doesn't, then they won't mix. So if they're alike, then they're going to mix. If they're not alike, they're not going to mix. And if you remember last year, we kind of compared polar substances to magnets versus nonpolar substances to marbles. And so we said if we have two different colored magnets and you try to mix them, they will mix because the north will attract the south from a different magnet. It doesn't matter what color the magnet is. What matters is you have opposite ends, just like the opposite charges here. If you have marbles, whether you have blue marbles or green marbles, they're all going to mix because it doesn't really matter. There's not that much attraction anyways. But if you try to take some marbles and some magnets and try to mix them together, the magnets will all clump together because they attract each other, and the marbles will just be sitting there. So we kind of compared it to like oil and water. The water particles are polar. They all attract each other, so they clump together, and the oil is just left there. So let's take a look at this question here. It says, which would be soluble in water and why? So CO2, would that be soluble in water? Well, CO2 is nonpolar, so the answer is no. And for now, we're just going to say because that's nonpolar, whereas water is polar, so they would not have strong interactions is what we would want to say. In this lesson, we're going to talk about what these interactions are called and which ones are strong, which ones are weak, and all that. But for now, we're just giving a simple yes or no. Ammonia. Ammonia is a polar substance, so that will dissolve in water. And again, for now, we're just going to say because the interactions between the ammonia and the water are going to be strong. We'll name what those interactions are in a second. Methanol. So methanol is polar. And so, yes, it will be soluble in water. Again, we'll just say for now, the interactions between methanol and water are strong. And then this is hexane. Hexane is nonpolar, and so that will not mix with water. You would say the interactions between hexane and water are weak. So let's talk more about more details about this solubility. So what happens when you make a solution? Well, so you have your solvent and you have your solute, right? And so in order to get the solute to dissolve in the solvent, where the solvent is surrounding that solute, three things have to happen. The first thing is that the solute particles need to be able to separate from each other. So the solute particles are attracted to each other with intermolecular forces, And so these solute intermolecular forces need to be overcome. We have to break apart, we have to overcome these attractions between the solute and other solute particles. Similarly, the solvent particles are also attracted to each other with these intermolecular forces. And so I need to be able to separate these solvent particles. So I need to overcome these intermolecular forces between the solvent particles. So I need to overcome the solute-solute intermolecular forces. I also need to overcome these solvent-solvent intermolecular forces. So I have to separate the solute particles and the solvent particles. And then I need to take each of my solute particles and surround it by solvent particles. That part is pretty easy to do because that's a favorable thing to do. I don't need to put in energy to do that. Energy is actually released when that happens because the solute particles and the solvent particles are attracted to each other, so they want to surround each other. So these two are not very favorable. I have to put in energy to get them to happen. They're hard to do. This is something that is favorable. It gives off energy, right? So in order for a substance to dissolve, the solute-solvent interactions, that attraction between the solute and the solvent, needs to be stronger than the sum of the solute and the solvent-solvent interactions. What does that mean? In order for this to be favorable, I need that attraction between the solvent and the solute to be stronger than the attractions between the solute-solute and the solvent-solvent. Because otherwise, if these attractions are stronger, then it's going to remain as a solute and a solvent separately. They're not going to want to mix because they're attracted to each other. The solvent particles are attracted to each other. The solute particles are attracted to each other more than they are to the solvent and the solute. And so we want the attractions here to be stronger than the attractions here and here in order for a solution to actually happen. So let's look at the different types of solutions or mixtures that we can make and the types of intermolecular forces that occur between them. So the first type of solvent-solute interactions is called ion-dipole forces. And all of these, by the way, they're going to have two different parts to their name. So regular, if I look at intermolecular forces within one substance, if I look at NaCl, for example, the particles of NaCl, the attractions between them, it's called ionic interactions. Or the attractions between water particles are called hydrogen bonding interactions, right? But if I mix NaCl with water, then it becomes ion dipole interactions, two words to describe it, because I have two different substances mixing together. So whenever you're mixing two different substances to make a solution, the solvent and the solute, we use one word to describe the IMFs of one and another word to describe the IMFs of the other one. So this would be for something that's ionic and polar mixing together. So for example, if I take NaCl and dissolve it in water, I would call the attractions between the NaCl and the water ion dipole. Ion because NaCl is ionic, so it has ionic interactions. Dipole because water is polar, and it has dipolar hydrogen bonding interactions. When we're mixing two things together, a lot of times we use dipole in general as opposed to specifying whether it's H bond or just a regular dipole. So let's draw a particle diagram of what's happening if I were to take one formula unit of NaCl. So if I have a crystal here of NaCl, so I'm going to say Na plus, Cl minus, Na plus, and so on. So there is an attraction between this Na plus and the neighboring chloride particles, right? Because the sodium ion is positive and the chloride ions are negative. If I take some water And my water looks like this, right? Where this is the oxygen, these are the hydrogens, right? The oxygen is partially negative, the water is partially positive. Sorry, the oxygen is partially negative, the hydrogens are partially positive. This is partially negative. There's an attraction between that sodium ion and that oxygen from the water, because the oxygen is partially negative, the sodium ion is fully positive. So if I have enough water particles gang up on that sodium ion and all these partially negative oxygens attract that sodium ion, that attraction can get strong enough that it is stronger than the attraction between that sodium ion and the rest of the crystal, the chloride ions. And so what happens is those water particles pull away that sodium ion. So now here's what it looks like. There's my sodium ion, and then I have a bunch of water particles surrounding it. And these water particles, I have the oxygen side facing the sodium. And here are my attractions. So these are called the ion dipole interactions, the attractions between the ion and the polar molecules. Now, once that happens, I clear the way for the chloride ion to be at the surface. And so now I take my water particles, and the hydrogen side of my water particles is going to be attracted to the chloride, because the hydrogen side of my water particles is the partial positive, the chloride is negative, so there's an attraction right here. And so if I have enough water particles with enough partially positive hydrogens to attract that chloride, I might be able to overcome the attraction to the crystal and pull it away. And so here's what it looks like. So chloride ions are a little bit larger than the sodium ions. And this time when I draw my water, I want to draw my hydrogens facing that chloride ion. And here are my attractions. And so again, those blue dashed lines, these are the ion dipole interactions. So this is showing just 1/4 million of NaCl surrounded by water or dissolving in water. A popular question on the AP exam is asking you to draw a formula unit of an ionic substance like NaCl dissolving in water. So basically to draw this. Make sure you keep in mind the size of the ions and the orientation of the water molecules around the ions. So you got to be careful that you draw them to size, so the sodium ion is smaller than the chloride ion. And also the orientation of the water particles. So you want the oxygen side of the water to be facing the sodium ion, and the hydrogen side of the water to be facing the chloride ion. So when I dissolve an ionic substance in water, two things happen: the dissociation and the hydration. The dissociation is basically the solute and the solvent particles separating from each other, which we've talked about here. So the ions separate physically, and the water particles separate as well. Right? So that's what we talked about earlier here. The ions have to separate from each other, so I'm overcoming these ionic interactions. And the water particles also have to separate from each other, so I'm overcoming those hydrogen bondings between the water. Then hydration also happens. Hydration is when the water surrounds the ions. And so that's this part of the picture here where the water particles are now surrounding the ions. So the dissociation is positive, right? In order to separate ions, I have to put in energy to overcome that attraction. In order to separate the water particles, I have to put in energy to overcome that hydrogen bonding attraction. But the hydration is negative because there's an attraction between the water and the ions. So when you bring two things that are attracted to each other close together, that releases energy. And so because one part is positive and one part is negative, my heat of solution or heat of dissolving or heat of solvation, those all mean the same thing, might be either positive or negative, depending on my numbers. So when an ionic salt is soluble in water, what that means is that the ion-dipole interactions, these attractions right here, between the ions and the water, those have to be stronger than the sum of the ion-ion interactions in the crystal in order to break that crystal, overcome those ionic interactions, and the dipole-dipole interactions between the water particles. So again, it's basically saying what I said earlier here. In order for this to happen, these attractions need to be stronger than these attractions and these attractions. Okay, so let's look at this question here. It says, which would be harder to dissociate and why? So these are all ionic. Which ones would be hard to dissociate the ions, to separate the ions, to overcome the ionic interactions between them? Well, since they're all ionic and we're looking at ionic interactions, remember ionic interactions have to do with charge and size. The higher the charge, the stronger the attractions. The smaller the size, the closer the particles are together, the stronger the attractions. And remember, charge trumps size. So Li2SO4 versus CS2SO4. So the first thing you want to look at is the charges. That's +1, -2, +1, -2. So those are the same type of charges. So then you look at the sizes. So the SO4 the SO4 anion is the same size, but between Li plus and CS plus, this is much smaller. And so if the ions are smaller in size, they can be closer, so you can have stronger attractions. So the smaller the size, the stronger the attraction. And so here I have stronger ionic interactions, harder to overcome, harder to dissociate. So the answer is lithium sulfate. Let's look at these here. So again, these are both ionic. And so which one would it be harder to dissociate the ions, to separate them? Well, you look at the charges. This is +2, -1, +1, -1. Stronger attractions here because you have higher charges. And so these are going to be attracted more strongly. And so it is harder to dissociate these ions. Let's look at the next question. It says, which would be more likely to have a hydrated cation? So the delta H of hydration has a higher negative value, like it's more favorable to hydrate it, to surround it with water particles. Well, the ones that are attracted to water more are going to be easily hydrated, right? So what does this attraction have to do? Again, all these attractions have to do with positive and negative attractions, right? Coulombic attractions. So the ions that have a higher charge and smaller in size will be attracted to the water more, because if there's a bigger charge, that's going to attract the partial positives and negatives of the water more. And if it's smaller in size, it's easier to surround with your water particles, right? So out of these two, we had already said that this is +1, -2, +1, -2, and we said that this has a smaller size, and so this would be easier or more likely to be hydrated, right? More favorable to be surrounded by water. Between those two, we said this is +2 and -1, +1 and -1, and so this has higher charges, and so can attract those water particles more, and you have a more favorable hydration. So if you look at this, you will realize that they cannot on the AP exam ask you which one is more soluble in water, right? Because they're kind of opposite of each other. So we're saying that the ones with stronger ionic interactions, where the ions are attracted to each other a lot because you have higher charges, let's say, these are really hard to separate. It takes a lot of energy to get them to separate from each other, the ions. But it also is more favorable to hydrate. It's more favorable to surround with water. Same thing with this one. These are harder to separate from each other, but it is easier to surround with water. And so the stronger these ionic interactions, the harder it is to separate the ions, but the easier it is to hydrate. And so they will not ask you which one is more soluble. They will either ask it like this, where they're only talking about the dissociation aspect or the hydration aspect, or they might tell you, hey, NaCl is more soluble in water than NiCl2. Account for that. And so if you're saying that NaCl is more soluble, you would say because it has weaker attractions, weaker ionic interactions, and so it is easier to dissociate it. Because remember, in order to dissolve it, you got to dissociate the ions and then hydrate. So if we're saying this one's winning, then you say, oh, well, that's because it's easier to dissociate. If we say this one is more soluble in water, then you say, oh, because it's easier to hydrate. So the hydration and the dissociation kind of go opposite. And so if they tell you that one thing is more soluble than the other, then you got to pick the reason why it would make it win, right? So if we say this is more soluble, it would be because it's easier to dissociate. So easier to separate the ions so that you can dissolve it. If they tell you this one's more soluble, then you say, well, that's because it is easier to hydrate. It attracts the water particles more, right? They will not ask you which one's more soluble. They'll just ask you to explain why one would be more soluble. Or they'll ask you for one aspect of the solubility. Okay, so that is when you have an ion dissolving in a polar substance, like NaCl in water. What if you have two polar substances mixing together? So we would call that dipole forces. So an example of that would be HCl in water, right? So both of these are polar, so we'd call the interaction between them dipole-dipole. So let's look at what that would look like. So let's say I have an HCl here. So this is partially negative, this is partially positive. Here's how it's going to be hydrated. So in around my hydrogen part of the HCl, I would have my water with the oxygen part facing the hydrogen, and then I'd have the hydrogen part of the water facing the chlorine. And here are my attractions. So the partial positive hydrogens are attracting that partial negative chlorine. And my oxygen part of the water, which is partially negative, is attracting the partial positive end of the HCl. So those blue things, those are the dipole-dipole forces, or dipole-dipole interactions. Forces and interactions in chemistry mean the same thing. They mean attractions, and so they're used interchangeably. Now, I do realize that you have hydrogen bonding in the water. You can, if you want, call it dipole hydrogen bonding forces if you want. But again, when it comes to mixing of two different substances, we can generalize and call it dipole, whether it has a hydrogen bonding or not. So if you want to call it dipole hydrogen bonding, you can. If it's HF in water, if you want to call that hydrogen bonding interactions, you can, or you can call it dipole interactions. That's fine as well. So either one. It's been popular on the AP exam asking about biochemical substances, so like big macromolecules like DNA and stuff like that. So in DNA, we do see some hydrogen bonding there. So these are base pairs, I believe is what they're called. My biology knowledge is not very good. If you remember, the C goes with the G and the A goes with the T. Remember that from the DNA base pairs. So the partial negative end of one molecule is attracted to the partial positive end of another molecule, and it has to be the partially negative one has to have a lone pair there, like that oxygen here, or that nitrogen here, and the other end that's partially positive needs to be a hydrogen that's bonded to a nitrogen or an oxygen or a fluorine. And so you see hydrogen bonding happening here. And so we'd say this is dipole interactions because there are two different molecules that have attractions to each other. And so these are called dipole interactions. If you want to call it hydrogen bonding interactions, you can as well. Again, we see a trend here. So when a polar solute is soluble in a polar solvent, that means that the dipole interactions between the solvent and the solute particles, so these interactions right here between the solute and the solvent, are stronger than the sum of the dipole interactions between the solute particles and the dipole interactions between the solvent particles. So what we're saying is that the attractions between the HCl and the water are stronger than the attractions between the HCl molecules and each other and the water molecules and each other. Okay, let's look at the third type of mixture here. What if you have two nonpolar substances? So for example, let's say you take some iodine and dissolve it in hexane. Both of these are nonpolar. And so another name for London dispersion is induced dipole. And the reason why we call it induced dipole is because if you remember, what happens is you have these molecules that are nonpolar with their electron clouds evenly distributed. And just by coincidence, if due to the random motion of the electrons are distributed in one area of one molecule more than another, that causes a momentary or instantaneous dipole. So you get a slight partial negative and a slight partial positive. What that does is it makes the other molecule neighboring to it do the same thing. So because this is partially positive here, now the electrons move this way. And so now you get both molecules that have a partial negative and partial positive, and now there's an attraction right here. And so this attraction is induced because one molecule forces the other molecule to move its electrons. And so we call this induced dipole. Again, induced dipole is another word for London dispersion. We just get fancy when we mix two substances together. Instead of calling it London dispersion, we call it induced dipole. So again, when a nonpolar solute is soluble in a nonpolar solvent, that means that the induced dipole interactions between the solvent and the solute are stronger than the sum of the London dispersion interactions between the solute particles and the London dispersion interactions between the solvent particles. Otherwise, the solvent and the solute would remain intact and they wouldn't mix together. So hopefully you're seeing a pattern here as we go. Okay, lastly, what if you get something that is polar with something that is nonpolar? So for example, if I take some iodine and I dissolve that in water, let's say. Now, we look at this and we say, oh, that's not really soluble, right? But in reality, remember, there's no such thing as insoluble. When we say something that's insoluble, that really means that it's slightly soluble. Just a tiny, tiny amount of it dissolves. And if you actually take some iodine and dissolve it in water, it doesn't turn purple like iodine and hexane, right? Iodine is purple in color. So when you dissolve it in hexane, you get this bright purple solution. When you dissolve iodine in water, you get like a brownish solution. So a tiny bit of it dissolves, but not a lot. And so that's because polar and nonpolar substances don't really mix, right? But again, it doesn't mean they don't mix at all. It's just a tiny bit of dissolving. So here's what happens. So if I have an iodine molecule here, and it is surrounded by water, right? Water particles are kind of randomly moving around it. If by coincidence, the water particles somehow line up this way, where there's a bunch of oxygen sides next to one side of the molecule and a bunch of hydrogen sides of the water next to the other part of the molecule. Remember that the oxygens are partially negative, right? And so, and these are partially positive. So what's going to happen is that just because of the polarity of the water, if it's lined up this way, because these are partially positive, it's going to attract the electrons in the iodine to migrate this way. So your electron cloud is going to get distorted, and you're going to get a very, very, very slight partial negative here, and a very, very slight partial positive here. And when that happens, you get an attraction between the positive hydrogen ends of the water and this part of the iodine molecule, and the negative oxygens of the water and this part of the molecule. Now that happens momentarily as the water particles are moving randomly. If they line up this way, then you get this attraction. But if they go back, because they're random, right, and they're not really lined up that way, then you don't get that attraction anymore. So it's just like Lambda dispersion, where it's on, then off, on, then off. It's very, 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 very weak. That attraction is very weak. And so polar and nonpolar substances do not really mix. So a nonpolar solute is not soluble in a polar solvent. The reason for that is because the dipole-induced dipole interactions, we call this dipole-induced dipole, dipole because one component is polar, induced dipole because one component is nonpolar. So remember, this just means London dispersion, right? So polar with nonpolar is what we're saying. So the reason why this is not soluble is because the dipole-induced dipole interactions between the solute and the solvent, so these interactions here, are very, very, very weak. They are weaker than the sum of the dipole-dipole interactions between the solvent particles and the London dispersion forces between the solute particles. Really, they are weaker than this, right? The water particles are so attracted to each other, they're not going to want to separate to surround the iodine. And so that's mainly why it doesn't dissolve, because these attractions are too strong. They are way stronger than the attraction between the solute and the solvent that we see. So very, very, very little of the iodine will dissolve in the water. All right. So, key thing here. It might get confusing, all this stuff. Basically, if you are asked for the intermolecular forces within one substance, you use one word, IMF. So if I'm asking you about NaCl particles and the attractions between them, you'd say ionic interactions. If I'm asking you about like HCl just by itself, so within the HCl particles, the attractions between one HCl molecule and another HCl molecule, you'd say dipole, and so on. So you use one word's descriptions if you are talking about like the molecules of just one substance. But if you are asked about the intermolecular forces between two substances, so you're mixing two things together, like in a solution, then you need to use two words to describe the interactions between the solvent and the solute. So because you have two substances, you use two words. So ion dipole, that would be like NaCl in water. Dipole dipole, be two polar things like HCl in water. Or H bond if you'd like. HF in water. Or H bond dipole. So these can be called dipole dipole if you'd like. But if you want to be more specific, you're welcome to use these. Or dipole induced dipole, or induced dipole induced dipole. So what I'm saying is if you're mixing two substances and you're talking about the interactions between them, you use two words. If you're only talking about one substance, you use one word. So we want to identify the intermolecular forces between the following. So we're mixing two substances, so we want to use two words. So you look at the two substances, you say, oh, this is nonpolar. This is also nonpolar. So this would be induced dipole, induced dipole. Right? Just within the CH4 particles together, there's London dispersion. Just for the C2H6 particles together, that's London dispersion. But you mix them together and we call it induced dipole, induced dipole. Next one, water and methanol. And so this is polar and this is polar, so you can call it dipole, dipole interactions. If you want, you can call it H bond interactions. That is totally fine. Either one of those is acceptable. So you can be specific or you can be broad when you're mixing two things. Okay, Li plus and H2O. Well, this is ionic and this is polar. So we'd call this ion dipole interactions. I2 and water, this is nonpolar. This is polar. So we'd call that dipole induced dipole interactions.